Okay, so today we're going to talk about generating functions, and they're not the only types of generators out there, as you can see from the clip art on this screen. Bad Religion also had a great album called Generator, and there was one that they produced called How Could Hell Be Any Worse, which may be a better subtitle for this particular chapter. Now, that's not the most useful information, but generating functions can help us to solve some counting problems, and they are definitely worthwhile in learning. So they represent sequences efficiently by coding the terms of the sequence as coefficients of powers of x in a formal power series. And again, the key idea here is they're the coefficients, not the value of the function. So the coefficients are the ones that come before the variables. And they can be solved to use or used to solve different types of counting problems. For example, number of ways to distribute objects of different kinds, number of ways to make change for a particular dollar amount using particular values of currency, solving recurrence relations, and proving combinatorial identities. I'm going to focus on the first two of these since we have a limited amount of time that we're working on this section. And I kind of want you to be able to solve those certain classes of problems, which are going to be useful for this class and for your further studies in computer science. So for a sequence, a formal power series whose coefficients are members of that sequence is a generating function. The generating function for the sequence A0, A1, AK, etc. of real numbers is the infinite series A0 plus A1 times X plus A2 times X squared plus A3 times X cubed plus A sub K X raised to the K. And so the A's are the sequence that we're interested in getting. This is sometimes called the ordinary generating function. So here's some examples. Match the sequences A sub k with their generating functions. And A sub k is equal to 3. Well, obviously, that's just going to have 3 as every coefficient. So that matches up to the sum from 0 to infinity of 3 times x raised to the k. And in general, for this one, each coefficient is going to be 3. How about A sub k is equal to k plus 1? That one corresponds to 2 raised to the k, x raised to the k. Or sorry, that one corresponds to k plus 1, x raised to the k, and a sub k is equal to 2k. It corresponds to 2k x to the k. So what about the generating function for the sequence 1, 1, 1, 1, 1? So this only has 5 terms. The generating sequence is going to be 1 times x to the 0 plus 1 times x to the 1 plus 1 times x squared plus 1 times x cubed plus 1 times x to the 4th plus 1 times x to the 5th. And we could rewrite that as x to the 6th minus 1 divided by x minus 1. Even though g of 1 is undefined, in this instance, we don't have to worry since the powers of x are only there as placeholders. So another example, let m be a positive integer. We let a sub k equal the m choose k for k is 0 through m, and that c is the choose function, which we covered, I believe, back in chapter 5 or 6 in CS141. So in general, g of x is going to be c of m choose 0, c of m choose 1 times x, c of m choose 2 times x squared, plus c of m choose m, x to the m. And so if you remember back, we had the binomial theorem, and that would be x plus y raised to the n is n choose j, x to the n minus j, y to the j. And so that will give us our sequence of values in that combinatorics identity. The function of f of x is equal to 1 divided by 1 minus x is the generating sequence for a series of 1s because 1 over x is equal to 1 plus x squared plus dot 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 is equal to the sum of k equals 0 to infinity of x to the k. Um, and that's whenever x equals 1. This is less of an example that you need to work through, but more of a useful fact. I suppose you could prove it, but you've already covered a lot of theory behind this in your calculus class. You can also look it up in table 1. You don't know about table 1 yet, but it's going to be probably the most useful thing from this section. So f of 1 divided by 1 minus a times x is the generating function for the sequence 1a, a squared, etc. And again, that's due to this combinatorical identity. And I can tell you this is also in that table 1 on page 489 of the textbook. You can add and multiply different generating functions. So if f of x is a sub k x to the k and g of x is b sub k x to the k, then f of x plus g of x is a sub k plus b sub k times x to the k, because you can factor out that x to the k. And the multiplication of them is the two nested functions. For you can also do extended binomial coefficients. So let u be a real number and k a non-negative integer. Then the extended binomial coefficient is determined by you choose k is equal to u times u minus 1 times that's u minus k plus 1 for k is greater than 0 and 1 if k is equal to 0. So you can do things like, what is the value? You have minus two things and you need to choose three. Well, with these extended binomial coefficients, you can actually solve that problem. And it turns out there's minus four ways to do this. If you have 1/2 thing and you need to choose three things from that, there are 1/16 ways to do this. So they're kind of nifty in that way, in that it will give a value to something that ordinarily wouldn't have a value, but it doesn't quite have the real world correspondence that we saw back in CS141. So let x be a real number with the absolute value of x is less than 1, and then let u be a real number. Then 1 plus x raised to the u, there's our coefficients. And so this is actually a more useful example of that. And when u is a positive integer, this reduces to the normal binomial theorem. So we can use that to get the coefficients for the powers when we raise 1 plus x to the u power. Find the generating function for 1 plus x to the minus m, where n is a positive integer, using the extended binomial theorem. And you can find this generating function through this and an application of example 8. And again, there's kind of a bizarre mix of notation here. I think it may be to make the page breaks, in the PDF work correctly, but I think the c n plus k minus 1 choose k x raised to k notation is more confusing than the standard notation. So table 1 is pretty darn useful, and it's not in the instructor's resources or the online slides, but it is actually in the textbook on page 489. And I recommend bookmarking it or a post-it note, or just printing that table out, because it's pretty useful for knowing what the different generating functions are and the different ones that you have to use. So here's table 1. I did take the trouble to scan it in, and it's in two different parts. So what can we use these generating functions for? Well, one area that we can use them for is solving different types of counting problems. And, not all lectures can be Hello Kitty, but we can occasionally have her as a guest. So generating functions can be used to solve a wide variety of counting problems. So they're particularly useful for solving R combinations from a set of n elements where repetition is allowed. So say I have some different numbers and I want them to sum to some constant c, like E1 plus E2 plus E3 is equal to 14. And then each E sub I may have some restrictions on it. we can actually use these generating functions to solve that type of problem. So let's take a look at an example of how we would use a generating function to solve that. So let's say E1 plus E2 plus E3 needs to be equal to 17. And E1 is somewhere between 2 and 5 inclusive. E2 is between 3 and 6. And E3 is between 4 and 7. So what we can do is we can basically write out the number of solutions. So for E1, it would be x plus or x squared plus x cubed plus x fourth plus x to the fifth multiplied by the values that E2 can take on, which would be the powers between 3 and 6, and multiplied by the powers that E3 can take on, which would be the powers between 4 and 7. And multiplying that out, I've done it in class before and done it on a sheet of paper just to show how it would work, but it's really better to get a computer or a tool such as Wolfram Alpha, or your favorite large language model to outsource this to a computation engine and do that type of work because there's quite a possibility. So the spoiler, if you've typed this in, is the coefficient of x17, which is the one that we want, ends up being 3. Uh, Another example, how many distinct ways can 20 identical cookies be distributed among the 11 students if each student receives at least one cookie, but no more than 4? And we'd often do this one in class, and the first student to come up with the solution would be the one who gets to distribute the cookies. So basically here, each student gets at least one cookie, but they can have no more than 4. So we would have x to the 1 plus x to the 2 plus x to the 3 plus x to the 4. And then we would raise that to the 11th power and find the coefficient of x to the 20th. And again, that's a lot of work, and it's better to put this into a computational engine than to try to do it with pencil and paper. At least I don't think I'd want to do this one with pencil and paper. How about the number of ways to insert tokens worth $1, $2, and $5 into a vending machine to pay for an item that costs our dollars when order doesn't matter? And again, if you're using $1, $2, and $5 bills to insert into a vending machine, doesn't matter if you put in the 2 first, followed by the 5, or the 5 followed by the 2. So the correct answer is the coefficient of x raised to the r, whatever the cost of it is. And then we would have 1 plus x squared plus x cubed for the 1s, 1 plus x squared plus x to the 4th for the 2s, 1 plus x to the 5th plus x to the 10th for the 5s. So when the item costs $7, obviously we're not going to insert more than $7, at least in ones that wouldn't be efficient, and wouldn't insert $8 in twos because, again, we'd have to give that back, and wouldn't insert more than $5 in fives. When we multiply this out, it takes about half a sheet of paper. And again, sometimes it's kind of fun to do this type of thing, but again, nice computational engine or tool will help you to work this out. And in this case, the answer works out to 6. When order matters, we're looking at the coefficient of x raised to the r in x plus x squared plus x to the 5th. And, here, the order in which you insert them matters. It matters if you insert the 2 before the 5. It matters if you insert the 5 before the 2. And then in this case, we would use identity 4 to get the generating function for that, and it would work out to 26 in this case. And in case you were wondering, 26 is really just 42, but it's in different units. So, if you guess 42 for this, you're probably spot on, just had to convert it over to the correct units. So we can establish some combinatorial identities, and this is the third application. The LifeLock is up here just because it's a, you know, I'm not sure why I had it up there, but LifeLock ran into some trouble. This guy actually advertised his Social Security and said, Social Security number and said, "Hey, nobody can, steal your identity." And turned out that somebody had stolen his identity and managed to get about $500 out of the deal. Um, LifeLock ended up tracking the person down and got him to sign a pre-typed confession and ask him to perform community service to the make up for his crime. But once police got word of it, they basically ended up having to throw out the case because LifeLock went ahead and did cavalier actions. So, in general, I would say don't advertise your social security number. Uh, Example 13 shows how you can show that n choose k is equal to n factorial divided by k factorial, n minus k factorial. That's one that you learned in CS141. And example 14 shows the R combinations from a set of n elements where repetition is allowed. And again, I believe that one was covered in CS141. And example 15 shows the ways to select R objects of different kinds when we have to select at least one. So we can use generating functions to solve recurrence relations, and that was the other topic that we had in this chapter. And the red pill here symbolizes a willingness to learn a potentially unsettling life truth. So here we go. And we can actually use these generating functions to find the solution to a recurrence relation and its initial conditions by finding an explicit formula for its associated generating function. So let's take a look at a specific example. So here's the recurrence relation. A sub k is equal to 3 times a sub k minus 1 for k 1, 2, 3, etc. With the initial condition a0 is equal to 2. So g of x is the generating function for a sub k, and we can multiply that by x. And then using the recurrence relation, we end up with a0 plus a sub k minus 3 times a sub k minus 1. X to the k is the generating function. And again, this works out because a0 is 2 and a sub k is equal to 3 times a sub k minus 1. And then we can actually use table 1 identity 5 to show that that is the correct generating function, where we have the 2 as a constant coefficient, and then 3 to the k, x to the k, which would generate the series of 3 raised to the k. Another example, earlier we had worked out enumerating valid code words that had an even number of zeros. In that example, we found that a sub n is equal to 8 times a sub n minus 1 plus 10 raised to the n minus 1. And then we can use generating functions like we did in the preceding example to find an explicit formula for a sub n. And following that line of reasoning, we get the same result that we got, I believe, in section 7.1. A sub n is equal to 1/2 8 raised to the n plus 10 raised to the n. And that's the end of the generating functions. Thank you so much for listening and joining me on this journey today.